This is part 2 of my series on single-factor ANOVA, analysis of variance. In this screencast, I'll be showing you how we can partition the sum of squares and create the ANOVA table. And I'll also show you how we can use Excel's ANOVA tool to perform this calculation. In part 1, I showed you how we can redefine each of our observations as an overall mean, mu, plus a treatment effect, tau I, plus some sort of random variation. So here we have for group I equals 1, each of our observations, these blue bars, can be cast as an overall mean plus our tau 1. Tau 1 is incidentally going to be negative, plus our epsilons here. The hypotheses to be tested, the most common one to use is this bottom one, the null hypothesis. All of the treatment effects are 0. The alternate, at least one of our treatment effects is non-zero. And so that's what we're going to test using analysis of variance. Similar to what we did in ANOVA with regression, we're going to partition the sum of squares. This entire circle represents the total variability. We can partition that. There's going to be variability due to random error, and we also have variability due to the treatments. For at least one of the treatments to be significant, we would expect most of the variability to be explained by the variability due to the treatments. So if you are to prove the alternate hypothesis that we set up, you really have to show that this red part of the total variability is much larger than variability due to random error. And that's what we do using ANOVA. We partition the total sum of squares into two parts, SST, that's the variability due to the treatments, plus the error sum of squared, and that's the variability due to random error. Recall from when we did ANOVA in regression, these sum of squares have different degrees of freedom, and so we kind of have to normalize by degrees of freedom. SST has capital N minus 1 degrees of freedom. The treatment sum of squares has A minus 1 degrees of freedom, and SSE has capital N minus A degrees of freedom. So SST equals SS treatments plus SSE. SST, as I showed earlier, can just be a sum squared of the residuals, Yij minus Y dot dot bar. Take each of those squared, and that's what SST is. SS treatments can be calculated by this first term on the right-hand side. We can just determine how far each of our treatment averages, that's what Yi dot bar is, from the grand average. We square that, we sum, and we multiply by little n, and that's what SS treatments is. And so when we divide by the degrees of freedom, we end up with the mean squares of the treatments and the error. We have two different scenarios. The first scenario is a large effect of at least one treatment. In that case, it would look more similar to what I have shown here, where the variability due to random error is a very small chunk of the total variability. Or we can have scenario 2 here, where the variability due to random error is approximately on the same order of magnitude as the variability due to treatments. And in this case, we could not accept the alternate hypothesis, and we would conclude that the treatment has no effect on the response. So in order to perform this hypothesis test and to show that the treatment level of at least one of our groups is non-zero, we're going to calculate an F statistic. If the two mean squares cannot be distinguished, then the ratio of MS treatments to the mean squared of error is going to follow the F distribution with A minus 1 numerator degrees of freedom and capital N minus A denominator degrees of freedom. If that test statistic is much larger than what would be expected if the two mean squares could not be distinguished, our test statistic F naught will be way up in the tail of the F distribution. And if this is the case, then we will accept the alternate and reject the null. So let's go ahead and do this for an example. I've got some computational formulas here, by the way. We can simplify SST and SS treatments. You see that these are a little bit different than what I showed earlier on this slide. For example, instead of having Yij minus Y dot dot bar squared for SST, there's a slightly more computationally friendly form of that that's shown here. We can just take Yij squared, so that's the sum squared of those, and then outside the summation, Y dot dot squared divided by capital N. Before we do this in Excel, I wanted to kind of show you the general layout for ANOVA. The general layout, we have the source of variation kind of in a different rows, the sum of squares in a column, the degrees of freedom, the mean squares, our F statistic, that's the ratio of mean squares, and then we usually calculate a p-value. Sometimes over here on the far right, we can calculate a critical F value. So you'll see that presented in some ANOVA tables. This ANOVA table is very similar to the ANOVA table we created using when we talked about regression. For single factor analysis, we only have the factor A and error and total. I've got this starter file called Burritos ANOVA Starter. I've got different cells named. I've got our formulas here. So we've got our replicates and our different treatment groups. Let's first calculate N. N is the number of replicates. We have 5 replicates. A is the number of treatments. We have 4 treatments. That's just the number of restaurants. And then capital N is just A times N. That's the total number of observations we have. And we have 20 observations here. Let's now calculate the sums. These are the yi dots. So this is just going to be the sum of all of those replicates for illegal Pete's. We can easily copy that over. So those are the sums. We can also calculate the averages. The averages are just the sums divided by little n. We can copy this over. We also need to calculate y dot dot. Y dot dot is the grand sum. And so that's just the sum of all of our treatment sums there. So we're adding up, and this is not the average, this is just the total sum. We calculate y dot dot because in these formulas here, these computational formulas for SST and SS treatments, we're going to use that. So let's use these formulas to calculate SST. SST is just the sum squared. That's what this double summation down here is going to do of all of our observations, our individual observations. And then outside that, we can subtract y dot dot. So I've named that y dot dot squared divided by big N. So I've named that capital N, big N. And so that means our total sum of squares is about 93,000. We can use this second formula down here to calculate sum squared of the treatments. That's equal to 1 divided by little n times sum squared of our yi dots. Our yi dots are the sums of our treatments. All right, so that's why we calculated the sums of the treatments up here. That's going to square each of those and sum them. And then outside, we're going to subtract y dot dot squared divided by big N. So that's that formula there. The treatment sum of squares is equal to about 80,000. Now I could, if I wanted to, compute total SSE. That's just the sum squared of the residuals. But we can calculate sum squared of the residuals because we can just subtract the sum squared of the treatments from the total sum of squared, and that gives us SSE. Now we're ready to fill out our ANOVA table. Let's first go ahead and put in the degrees of freedom. As you recall, the total sum of squares has capital N minus 1 degrees of freedom. The treatments have A minus 1 degrees of freedom, and error has capital N minus A degrees of freedom. Degrees of freedom of treatments is A minus 1. Error has big N minus A degrees of freedom, and SST degrees of freedom, big N minus 1. And you can just check that the treatments plus error degrees of freedom add to the total. Here I'm just going to type in SS treatments, SS treat, SSE, and SST that we calculated earlier. Mean squared is simply the ratio of sum of squares to the degrees of freedom, so we can just do that. I can simply copy this down. We can compute an F statistic. Again, what we're doing here is we're calculating this F statistic, the mean squared of treatments, divided by mean squared of the error. And that's simply MS of the treatments divided by MS of the error. And our F statistic is 33.89. We can compute a p-value for that. We need to compare to the F distribution with A minus 1 numerator degrees of freedom and capital N minus A denominator degrees of freedom. So I can type in f.dist.right-tailed because we're looking at a upper-tailed test. Our test statistic as the first argument. We have A minus 1 numerator degrees of freedom and big N minus A denominator degrees of freedom. And we get a p-value of about 3.6 times 10 to the negative 7th. What we can conclude here is that, this is basically a slam dunk. That p-value is so small. Our conclusion, really the only thing we can conclude is a choice of restaurant or has an effect on burrito mass. And that's really all that we can conclude here. And just to finish this, let's just calculate a critical value that we would have to exceed in order to accept the alternate hypothesis. And sometimes you'll see this F critical presented in the ANOVA table, sometimes you don't. F.inv.rt, the probability is alpha. We have a minus 1 numerator degrees of freedom, big N minus a denominator degrees of freedom. So that's 3.24, and we're up at 33.89. So just to finish off the ANOVA table, let's put in that F crit. In the next screencast, I will show you how to do pairwise comparisons for the different treatment groups. Thanks for watching.